In this section, we talk about the pumping lemma of regular languages. All regular languages have this pumping property. If a language does not have this pumping property, then it is not regular. Because all regular languages have this pumping property, and if some language does not have this property, then for sure it is not regular. For this reason, the pumping lemma is usually used to prove a language is not regular. And it can only be used to prove a language is not regular. It cannot be used to prove a language is regular because some non-regular languages also have this pumping property. So even if you have proved that a language has this pumping property, you don't know if this language is regular or is among those few non-regular languages which have this pumping property. Alright, what is pumping lemma? If A is a regular language, then there exists a number P, which is a natural number, such that for all strings S in A of length at least P, it is possible to divide S into three pieces, S equals XYZ, satisfying the following conditions. First, for each I greater than or equal to 0, X y to the I, z is in A. This means we can pump y for I times. Since I is any number greater than or equal to 0, this means we can pump this y for any number of times, and the resulting string is still in the language. This property also needs to hold for I equals 0 and I greater than 1. When I is equal to 0, we say we pump the string down. When I is greater than 1, we say we pump the string up. This is the first condition. The second condition is y is a non-empty string. Because if y is empty string, then S equals XYZ can be written as XZ. And for any number I greater than or equal to 0, this xy to the I, z is equal to xz. Because S is in A, then if we pump this empty string many times, the resulting string is still equal to S, and thus is still in the language. So in this case, we did not say anything. We take a string S in A, and we multiply S, but after the multiplication, the resulting string is still S. For sure, it will be in A. It's not a different string. We are still talking about the same string. So this is trivially true. And it's useless. So we require this y be non-empty. The third condition is the length of xy as a whole is less than or equal to p. This means we need to pump S early. Let's analyze a few details of this pumping lemma. It says there exists a number p such that all strings S in A of length greater than or equal to p can be pumped. It doesn't require any number or all number p to satisfy this property. It only says some p satisfy this property, then that's good enough. But for such a p, it should ensure all S in A satisfying this property of length greater than or equal to p can be pumped. All strings satisfying this property need to be pumped. S can be pumped means there is a way to divide S into three pieces, and we pump the middle piece for any number of times. We only need to find one way such that this S can be pumped. We don't require S to be pumped in any possible way. Now let's talk about the procedure of using pumping lemma to prove a language A is not regular. We do this by proof by contradiction. The procedure of proof by contradiction is you assume the opposite of what you want to prove, then you develop a contradiction. Thus, we can make a conclusion that my assumption was false, and the original statement should be true. So in the first step, we assume A is regular. The second step is to use the pumping lemma to guarantee the existence of a pumping length P such that all strings in A of length P or greater can be pumped. We don't know the exact value of P, so we state it as a general number, not a specific number. Then the next step is to break this pumping lemma on this language so that we can reach a contradiction. We break the pumping property of A by showing that for any possible value of P, there exists a string in A with length greater than or equal to P. And for any possible way to decompose S into XYZ, satisfying two conditions, XY as a whole has length less than or equal to P, and Y is non-empty. We show that in any possible way to decompose S into XYZ, there exists a number I greater than or equal to 0 that will make the pumping property fail. That means if you pump this Y for I many times, the resulting language is not in A. The critical part in developing a contradiction is choosing an S and a value of I such that this S cannot be pumped I times. And that's what we do in step 3 and 4. In step 3, we find a string S in A satisfying the property that it has length greater than or equal to P. And we need to choose a specific string S. Since P is a general number, and we want to show that all possible values of P does not work, so we need to express S in terms of P. And if we can show this S cannot be pumped, then we have shown that for all possible values of P, there exists such an S, such that this S cannot be pumped. So this S is specific in this way. It is expressed using P. It cannot be too specific. For example, you say S equals 0, 1, 0. That's too specific. After choosing such a string, we demonstrate that S cannot be pumped by considering all ways of dividing S into X, Y, and Z, satisfying condition 2 and 3. We usually use condition 3 to eliminate some cases of X, Y, Z. Because in this part, we need to consider all cases of dividing S into X, Y, Z. There can be many cases if we don't apply this condition 3. Since we need to consider all ways of dividing S, the cases need to be exhaustive. And in each case, we need to find a value I. This I is not equal to 1, such that x, y to the I, z is not in A. This means we cannot pump this string I times. If we pump that I times, then the resulting string is not in the language. By pumping lemma, this resulting string should be in A, but we show that it's not in A. So a contradiction is formed. Popular values of I are 0 or 2. When I is equal to 0, we pump the string down. When I is equal to 2, we pump the string up. Finding a string S that works for steps 3 and 4 is challenging. One string doesn't work does not mean another string will not work. So if some string does not work, just try to find another string. Alright, so we use pumping lemma to prove a language is not regular. If a language A is regular, then all strings S in A with a length greater than or equal to P can be pumped. But if A is not regular, then it is possible that some strings in A can be pumped and some strings cannot be pumped. It's possible that both strings exist in this non-regular language. Now let's apply the procedure to prove a language is not regular. This language is a set of strings over the alphabet A, B. And the strings in this language has this property. The number of A's in S is less than the number of B's in S. We prove this is not regular. And we do that by proof by contradiction. So the first step is always assume this language is regular. Then the second step is to apply this pumping lemma on this A. So by pumping lemma, there exists a natural number P such that for all strings S in A with a length greater than or equal to P, there exists X, Y, Z over the alphabet, satisfying S equals X, Y, Z, and the length of X, Y is less than or equal to P. Y is non-empty, and for all possible values of I greater than or equal to 0, we can pump this string for I times, and the resulting string is still in A. The third step is to find a string in A with the length greater than or equal to P. So the string we choose is A to the P, B to the P plus 1. A to the P means there are P copies of A. This string is in A because the number of A's in S is equal to P, and the number of B's in S is equal to P plus 1, and P is less than P plus 1. So this string S is in A. You need to give the reason why this S is in A. And you also need to show this S has length greater than or equal to P. In this example, my S has 2P plus 1 symbols. So the length 2P plus 1 is greater than or equal to P. This string satisfies our property. First, it's in this language. Second, it has length greater than or equal to P. By the way, this A to the P, B to the P plus 1 is a special case of the general rule. The number of A's in S is less than the number of B's in S. Of course, you can choose another string that satisfies this property. For example, A, B to the P, A. But I choose this A to the P, B to the P plus 1 because it cannot be pumped. So the fourth step is to show that this S cannot be pumped in any way. In this step, we decompose S in any possible way into X, Y, Z, satisfying these two conditions. The length of X, Y is less than or equal to P, and Y is non-empty. Now we need to consider cases, because we say we decompose S in any possible way. So we consider all cases of decomposing S. To decompose S into X, Y, Z such that the length of X, Y is less than or equal to P, this implies my Y is of this form. It is A to the K for some K greater than 0 and less than or equal to P. This is the only case to consider in my example. But in general, you need to consider multiple cases. What is the value of this Y? And in each case, you need to find a value of I such that this S cannot be pumped I many times. The I choose here is 2. Then the resulting string X, Y to the 2, Z, is equal to X, Y, Y, Z, and it has the form A to the P plus K, B to the P plus 1. Because I have pumped this Y twice, pumping Y once will give the original S. If I pump that twice, that means I have inserted K copies of A into this string. So I will have P plus K copies of A. Here, you also need to consider cases for this resulting string. It is possible that the length of X, Y is less than P. In this case, the form of Z will be some number of A's and then P plus 1 copies of B's. But in this case, the resulting string X, Y, Y, Z is still of this form, P plus K copies of A followed by P plus 1 copies of B. Another case is that X, Y has the length P. In this case, Z will only have P plus 1 copies of B, and Z will not have any number of a's. In this case, x, y, y, z still have this form p plus k copies of a and then p plus 1 copies of b. And we don't have any other cases for this resulting string. Since in both cases, the resulting strings have the same format, we can merge these two cases into just one. But still, when you consider cases here, the cases need to be exhaustive. You need to consider all possible format of this resulting string. Now back to pumping lemma. If I pump this y twice, the resulting string should still be in this language A, but it is not. Because k is greater than 0, this means p plus k is greater than or equal to p plus 1. That means the number of a's in this resulting string is not less than the number of b's in this resulting string. So this resulting string violates the property of strings in this language A. We have shown that a resulting string should be in A, but it's not. Thus, a contradiction is formed. So we can conclude that the assumption is false and A is not regular. For these 5 steps, step 1, 2, and 5, you can just copy these 3 parts in your proof because you always need to provide these 3 parts. The critical parts are 3 and 4. In step 3, we need to find a string and show that that string is in A and that string has length greater than or equal to P. In step 4, we decompose this string in any possible ways into x, y, z, and in each way, we provide a value of I and show that S cannot be pumped by this I many times. You can choose different values for I in different cases. When you show the resulting strings cannot be pumped I many times in each case, you need to give the reason why it cannot be pumped I many times. You show that the resulting string violates the property in A. And usually you need to consider cases for this resulting string. Alright, that finishes the proof of A is not regular. This is one example. Think about this example if I change the property of A. Let's say A is still the set of strings over A and B. Now the property of the strings is the number of A's in S is greater than the number of B's in S. And you need to prove that this A is not regular. So the critical part is to choose an S and an I. In this case, A to the P, B to the P plus 1 is a good choice. Because this property is symmetric to the property we have shown in the example. In the example, we chose A to the P, B to the P plus 1 because we want more B's. Now, since we need more A's, I choose A to the P plus 1, B to the P. And we want to show the pumped string is not in this language anymore. So we need to pump down so that the number of A's is not greater than the number of B's. That's why we choose this value for I as 0. By pumping y 0 times, it's equivalent to remove that y from this S. Since y is not empty, the resulting string will have less than or equal to p copies of A's. And that violates the property of strings in this language A. Now let's think about what if the property is the number of A's in S is equal to the number of B's in S. Well, in this case, I can choose S equal to A to the P, B to the P, because we want the number of A's equals the number of B's. And I can choose either I equals 0 or I equals 2. For I equals 0, I pump down. That means I will have fewer A's than B's. For I equals 2, I pump up. That means I will have more A's than B's. Now let's consider another example. Now the language is over a unary alphabet 1, and it contains the set of strings of this format, 1 to the n. This n is a prime number. So each string in this A should have a prime number copies of 1s. We prove this A is not regular by contradiction. So the first step is to assume the opposite of what I want to prove. So we assume A is regular. Then the second step is apply pumping lemma on this A because it's regular. By pumping lemma, there exists a natural number p such that all strings in A with a length of p or greater, it is possible to divide this S into three parts, x, y, z, satisfying two conditions. X, y has a length less than or equal to p, and y is non-empty. And for all possible values of I greater than or equal to 0, we can pump this y for I many times, and the resulting string x, y to the I, z is still in A. Now comes the critical part. Choose the string S in A, which has length greater than or equal to p. This S needs to be expressed in terms of p. In the previous example, we express S as a to the p, b to the p plus 1. So it's expressed in terms of p. Now I choose my S to be 1 to the n. That means I have m copies of 1s. But this m needs to be expressed in terms of p. So the property of m is a prime number, and m is greater than or equal to p. After choosing this S, we need to show this S is in my language A, and this S has length greater than or equal to p. Clearly, this S is in A with m being a prime number, and the length of S is m. Since m is greater than or equal to p, my S also satisfies the condition of length greater than or equal to p. But you always need to give the reason why S is in the language and why S has length greater than or equal to p. In the next step, we need to show that in any possible way to decompose S cannot be pumped. So we decompose S in any possible way into x, y, z, satisfying two conditions. The length of x, y is less than or equal to p, and y is non-empty. Now we need to consider cases. What's the value of y? Well, in this case, because my string only has 1s, so there's only one case for y. Y is of the form 1 to the k. There are k copies of 1. But this k has some property. It's not any number. K is greater than 0 because my y is non-empty. And k is less than or equal to p because the length of xy is less than or equal to p. So this k has this property, greater than 0 and less than or equal to p. Again, in this part, it's general to consider several cases, so those cases can be exhaustive. But in my example, it is a special case because I only have one case, and that one case is exhaustive. If you have multiple cases, then you need to choose a value I in each case and show that the string cannot be pumped that many times. And this I can be different in different cases. Since I only have one case here, I only need to choose one value for I and show that this S cannot be pumped this many times. I choose this I to be m plus 1. Why do I choose this number? Because I want the resulting string x, y to the I, z be a string not in the language. If I analyze this resulting string, it has the form x, y, y to the I minus 1, z. This means I insert I minus 1 copies of y into this string S. As a result, the total number of 1s is m plus I minus 1 k, because each copy of y has k ones. And I want this resulting string not in A. So I need this number m plus I minus 1 times k be a non-prime number. So I choose I equals m plus 1 because in this case, the resulting string will have m plus mk copies of 1s. If you analyze this number, m plus mk, it can be written as m times k plus 1. Well, a number is prime if it cannot have any other factors other than 1 and itself. Now we have shown that this number, m plus mk, it has two other factors, m and k plus 1. And this k plus 1 is not equal to 1 because k is greater than 0. And this k plus 1 is not equal to m plus mk because k is less than or equal to p. So this number m plus mk has two factors other than 1 and itself. So this number cannot be prime. If this is not prime, then 1 to this number is not in the language A. So up to now we have shown that a string s is in A, and if we pump this s m plus 1 times, the resulting string should be A, but it's not. So that's a contradiction. Now we can conclude the assumption is false and A is not regular. After these two examples, I hope you have a better understanding of pumping lemma of regular languages. The challenge part is to choose an S. There is no shortcut to it. You have to practice more. Try many proofs. And the pumping lemma is a long statement. A good way to remember it is to write it many times. And each time when you write, you read along so that you understand each segment of the lemma. Leave a comment if you have any questions.